country. Hi, Chris.
Hi.
Chris, have you missed our country?
Can you hear me well?
I can hear you. Do you miss our university?
I cannot hear very clearly what you say, but it's okay. Looks like you're.
Good morning.
Morning.
Morning.
Okay, so am I supposed to start?
Okay, we are. Yeah. Okay, we are starting section 3. Before start, I would like to welcome to you, all of you, in 10th IC Smart Grid Conference. And also I would like to thank the organizer, Professor İlhami Çolak, Professor Krukova and Sagaroğlu. They are organizing such a good conference this year also. And I would like to welcome to Matsui, Professor Matsui also. We are sharing together this session. And before starting the keynote speaker, I would like to introduce him a little bit. Professor Mi is the professor at the chair of the Department of Electric and Computer Engineering in San Diego University. He is a fellow IEEE and Society of Automotive Engineers. He is also director of the U.S. Department of Energy founded Graduate Automotive Technology Education Center for Electric Drive Transportation, San Diego State University. He was the previously faculty of member of the University of Michigan Dearborn from 2001 to 2015, and the electrical engineer with the General Electric from 2000 to 2001. He also served as the CTO of One Power Solution from 2008 to 2011. Dr. Mi received his PhD from University of Toronto, Canada in 2001. Dr. Mi has won numerous awards, including the Distinguished Teaching Award and Distinguished Research Award from the University of Michigan Dearborn, IEEE Region 4, Outstanding Engineering Awards, and IEEE Southern Michigan State Outstanding Professional Awards, and SAE Environmental Excellence in Transportation Awards. He is the recipient of the 3 Best Paper Awards from IEEE Transaction on Power Electronics and the 2017 ECCE Student Demonstration Awards. In 2019, he received the inaugural IEEE Power Electronics Engineering Technology Awards. In 2022, he received the Albert W. Johnson Lecture Awards, to name it the Distinguished Professor, the highest honor for any given to San Diego State University faculty member, and only one award is given each year. Dr. Mi has received over $5.8 million in the research funding since joining San Diego State University in 2015. He has published 5 books, 204 journal papers, 126 conference papers, and 20 used and pending patents. He served as editor-in-chief, area editors, guest editor, and associate editor of the multiple IEEE transaction and international journals, as well as the general chair over the IEEE International Conference. Professor Matsui, can you say something do you want to say something before starting his speech?
Thank you very much, Professor Gruber. So please start, Dr. Chris Mee.
Okay. So thank you very much. Thank you for the invitation. It is my pleasure to present this keynote speech at such a wonderful conference. But I saw that our program is delayed by almost 30 minutes, and which means also I have to catch a flight right after this. So I probably keep my presentation within about 30 minutes. So can you all see my screen? Can you see my screen?
Yeah, we can see.
Yes, okay. Okay, so today I will talk about the cost-effective integration of second life UV batteries with solar PV systems. The reason about this talk is that electric vehicles have been becoming more popular these days, especially due to the high gas price. But the battery only lasts about 8 to 10 years. What are we going to do with those batteries? So apparently, one of the way to mitigate the environmental impact and reduce the cost of the EV system is to use these batteries for second life. So let me start with where I come from. San Diego State University is located in San Diego, California, near the Mexico border. And we are very close to the city, about 50 miles east of the city. And we are built on a hill. It's a very nice campus. I welcome all of you to visit us if in the future that you have an opportunity. And I also recruiting graduate students to join my program. So if anybody is interested, you're welcome to contact me after the presentation or in the future. So the background is like this. Now we are promoting energy storage systems for grid storage. In particularly because of what we have with the renewable energy generation, which are not stable, such as solar and energy. Let me see if I can do this in a little bit different way. Okay, minimize the and the need for these storage systems are rising very rapidly. But the problem is that these batteries are expensive, and the installation of such systems may not make economical sense. So on the contrary, second life UV batteries, those include from discarded UV batteries and UV replacement and others, and so vehicles, they're available. We can certainly send them for recycling, but that will shorten the life cycle of the battery. So it's better that if we use them for secondary storage. I see a lot of noise. Maybe somebody can mute your phone, mute the microphone. If you're not speaking, yes, thank you. But the barriers to your second life battery is that we need to develop and integrate these batteries reliably, cost effectively, and economically. So it must be safe and consistent, and we must overcome a few hurdles, like the proper removal from EV, transport them, storage them, testing them, selection of them. We need to find a quick, simple, and accurate method, and we need to do a dynamic battery management so that we can minimize the degradation, so this battery can last a meaningful length in their second life. So the scope of our work, which is sponsored by the California Energy Commission, start the aging study in the laboratory of this second life battery, and we create a second life battery genome through laboratory scale analysis. We develop a battery management system, which includes the technologies, algorithms, operation strategies, which can increase overall efficiency, reduce total ownership cost, and decrease degradation. We will design and we're in the process of deployment of 2 pilot testing facilities to demonstrate that these technologies make sense. So the first step of our job is to do the characterization of second life UV batteries. And we did study on 4 different kinds of UV batteries. That included the Nissan Leaf, which is a very popular battery, the Gen 1 battery, and also their Gen 3 battery. And we also studied the lithium iron phosphate battery used for forklifts, and also the last kind is also lithium iron phosphate battery for the buses. And our conclusions are shown in this bottom of each figure. And you can see that after testing 100 packs, we found that the Nissan Leaf Gen 1 battery is good for storage application. The Nissan Leaf Gen 3 battery is lithium, nickel, manganese, and cobalt type battery. They are good also for second life. The lithium iron phosphate battery on the right hand, they are okay, but we need to balance because all the battery cells are not balanced after many years. So we were forced to have to balance these batteries before we put them in storage applications. The conclusion here is summarized. As you can see, the Nissan Leaf 1 and G3 batteries, they're good for second life, and they can last for roughly 10 to 15 years in their second life. The electric forklift and electric bus battery, they both have a serious balance issue. If we can address the balance issues, and this battery can also last for another 10 to 20 years in their second life. So we have developed a technology to address the balance issue in these battery packs. To start with the Nissan Leaf Gen 1 battery and Gen 3 battery, as you can see, we tested many of those batteries, including the pack and the battery cell and the battery module. For example, we assembled the battery pack to get the battery module and the battery cells we need for the laboratory aging test. And then we put these batteries inside the laboratory. We do the aging test using the cell cyclers like Abin and chroma testing cyclers. And we also put them in a summer chamber to test their performance under different temperature to make sure these batteries can last as they're supposed to in real life applications. The results of the Nissan Leaf Gen 1 battery shows very linear degradation of the battery in terms of their capacity. The internal impedance, however, at the bottom figure shows a slightly nonlinear increase over time. So by the time the internal impedance doubles, we think these batteries are good to go to the recycling facility because their internal loss was slightly increased and the efficiency is no longer meaningful. The Nissan Leaf Gen 3 battery, however, shows a faster degradation after a certain amount of time. If I go back one slide, you can see the degradation of Gen 1 battery, the top graph. It shows very linear degradation. There's no aging need. Therefore, you can still use them if you want, but just that their efficiency is not as good. But for the Gen 3 battery, they have a knee point. All the batteries demonstrate some sort of knee point after a certain number of cycles, typically around 1200 to 1600 cycles. After the knee point, these batteries degrade very dramatically, and the internal impedance, as shown on the bottom graph, increase dramatically, which means the knee point is where we need to stop these batteries. Otherwise, not only just the efficiency is no longer good, but the internal impedance is very high. It creates a dangerous condition for the batteries to be continuously used. Therefore, we need to develop algorithms, as you can see later on, to detect the knee point of these Gen 3 batteries. This is because the LMC battery, the intrinsic performance of these batteries. We also tested the Gen 3 module to make sure that this cell testing are consistent because we disassembled them. After the module testing, we confirmed that the cell and the module degradation are very similar. So therefore, it confirmed that this study makes sense. And this is the testing of the cell testing of the lithium iron phosphate battery from the electrical forklift. As you can see, the lithium iron phosphate battery shows, again, a very linear degradation for the capacity and also a slight increase in terms of their internal impedance. Because there's no knee point, these batteries can last a long time in their second life. The knee point detection is very important for the Gen 3 battery, for the lithium, nickel, manganese, cobalt battery, because after the knee point, these batteries should not be continued in their second life. But we have to find a method to detect the knee point. So this is where we did in terms of how we identify the knee point of each battery cell inside the system. And we detect the change of the capacity, and we detect the linear degradation. And at some point, it will show a knee point as shown on the right diagram. And you can see that the knee point is clearly identified. Now we need to remove these batteries from their system application. So after the laboratory testing, we will develop these systems using the exact pack in 2 pilot testing sites. The testing sites were deployed, including this 2. So on the left hand, you can see we have 8 battery packs, and each 4 battery packs are connected to 1 DC-DC, which has 4 channels, independent channels. So basically, we have 8 DC-DC converters, 8 battery packs, and 1 inverter. The inverter supplies AC to the building. On the right hand, you see we have 4 batteries for a smaller building. So each battery is connected 2 channels of a DC-DC converter. So we still have 8 channels of DC-DC, and the output of this DC-DC are connecting parallel to an inverter. And both systems output 208 volts 3-phase AC to the building. One of the important work in order to do the deployment is to develop a BMS gateway, because the battery pack comes with the gateway. However, because we use many packs in the system, they all send out the same information with the same ID. We cannot differentiate the signals if we connect them all together in the same signal cable. So we need to develop this gateway to take the input from the BMS. So each gateway is connected to each BMS, and they look for the information. They identify each information and stamp them with the ID, and that is going to be sent to a central controller. So we have designed this gateway for each BMS, each battery pack. And then we have to design the mechanical system, including the container, the structure to hold the battery, the structure to hold the power components, and the installation as well as cooling system. So this is where we develop the battery container to hold up to 15 batteries inside each container using just the generic shipping container, a 20-foot long. And then we design the structure to support the battery, because these battery packs are very heavy, up to 1,100 pounds. And the support has to be able to hold the battery, and also has to sustain like earthquake and other events. So we designed the support system, and we verify the strength of the system using simulations. So in order to optimize the application of this battery, such as maximize the benefits and maximize the life cycle, we have to develop some optimization and control strategies. The strategies include this modular energy management system. The energy management system will collect information of the battery, the inverter, the DC-DC converter, the solar system, as well as the building usage. Based on all this information, we will optimize the charge and the discharge of each battery at what time and at what amount. By doing that, we're able to maximize the benefits of the system to the owner, so they can save maximum amount of money by installing these systems, as well as extend the life cycle of these batteries so that it can last as long as possible. So this is a multi-objective optimization system problem. And we did, for example, balancing of the battery cells and the battery packs, because without the balancing, the battery pack would degrade quite quickly, because some cells would degrade quicker than others. And then we designed the aligning operation. In case there's a power outage, we'll be able to disconnect the battery and the solar system from the power grid, and we supply power to the building using the battery and the solar only during the day, and in the evening we'll supply power to the building using the solar system only. And we also developed a phone app so that we can monitor the system performance remotely. And this phone system is able to monitor all the information such as the battery cell voltage, the pack voltage, the charging SOC, SOH, the solar generation, and the building usage. We can also have an emergency stop of the system in case anything happens from remotely. And finally, we designed a system to optimize the control. For example, we use model predictive control to control the battery charging. Based on the study, we found that without MPC, the system total charge is $2,092 per month for the electricity. After using MPC, we can reduce almost 200 to something like $500 per month, which is almost average 25 to 30%. So this is very good for the owner because they can save cost of their system. For any building, based on their usage, we design this software algorithm to design the size of the battery. Because if you put too much battery, it costs too much. The return is very long. It's not economical. If you don't put enough battery, the cost savings is not very obvious. So we designed this sizing optimization algorithm to decide the size of the battery based on the building usage, the solar generation, and other factors. The pilot testing sites are under construction. And we have select two sites. So one site estimate can save roughly 3,000 per month or 36,000 per year. The cost of the system is 96,000. So which is going to save 300,000 over the lifetime, which makes a lot of sense. However, the second building doesn't save that much because the smaller building doesn't use as much energy. However, this system provides power backup during outage. This bio building will lose a lot of money if there's a power outage. The estimate is that if the power outage is 24 hours, they will lose $100,000. Therefore, this power backup operation makes a lot of sense for the owner. We have connected all the battery from Nissan, our pilot test, and we have designed the site. This graph shows the parking lot. On the top graph, on the top part, you can see in the corner, top right corner, we're going to be put the container. We're going to run a conduit from the container to the building. The container is going to be a little bit distant from the building. In case something happens, it's not going to impact the building operation. And then inside the container, we have 6 batteries for this site, and we have the inverter, DC-DC converter, monitoring system, and circuit disconnectors. This shows how we connect the battery with the solar and with the power grid. And that is basically what we are going to deploy in the next month and a half. In the meantime, I also want to show you what I do, our group research other activities. One of the activities is our wireless charging system. We do this wireless charging system for our electric vehicle. We do battery management system. As we know, batteries catch fire once in a while. So our study is trying to identify, diagnose the system so that we can potentially prevent the catastrophic event to happen in the field. And the study included many aspects of the battery management system, including cell balance, state estimate, charge control, cell monitoring, safety, and solar management. And we also developed an offline cloud-based algorithm to monitor the battery and to diagnose the battery for any system, like grid energy storage system, as well as with batteries. In my group, we also conduct studies for vertical takeoff and vertical landing airplane. The reason we do this because we can develop this airplane that can take off vertically and land vertically. Not only that, they can travel very fast. Currently, the emergency access, for example, for medical personnel transportation, for human organ transplant, they use helicopters. The problem with helicopter is that they're very noisy, they're very big, and they travel very slow. With these airplanes, they can vertical takeoff, vertical landing. They're not that noisy. They need a small platform. They can travel very fast. They can carry like 4 to 6 people, 5 to 600 pounds of goats, so they can be used for medical service, emergency transportation, for rescue, and for many other applications. So this program is still in progress. In my group, we have published a number of textbooks in this area. So if you have an interest, you're welcome to look at them. And also this YouTube channel, which has a lot of information about our research, and also their education modules developed by other professors at this channel. So you're welcome to look at them. And finally, if you work in the wireless power charging area, there's a wireless power conference next week in Bordeaux, France, and there's another one in San Diego, June 7 to 10 next year. So you're welcome to join us next year. With that, I will stop my presentation, and I'll be able to answer a few questions, and then I have to take off for my flight. Thank you very much.
Okay, Matsui. You can collect question.
Okay, so is somebody a question or comment, please? Do you have a comment or a question?
You're always welcome to contact me via email or WhatsApp. And
so may I have one question? Okay.
Sure.
Thank you very much. So, Professor Mi, the presentation is a very interesting topic. So my the use of the battery is important for the saving energy resource.
Yes.
So my question is, could you tell me how to evaluate reliability of the second life battery? Because second life battery is very old one.
Yes. So basically, the second life batteries are what happens when the vehicle owner doesn't like the driving range or the power. So they will go somewhere, have the battery disassembled, and those can be collected at the shops like car dealerships and repair shops and so on. And these batteries have to be transported to a central place to be tested for their current state. If their current state, for example, is about 70%, we can use them for secondary storage. If their capacity is already very low, like 50%, or if their internal impedance is pretty high, and then they should be sent to recycling.
Okay.
Yeah.
Thank you. So any other question?
Okay. So if no questions, I think it's a good time for me to close because I do have to taxis waiting for me.
Thank you. Thank you very much, Chris.
Thank you all. See you later. Bye-bye.
Thank you.
Okay, we are closing the session and we have lunch break. See you again.
1 hour later.
Okay, 1 hour. We will meet 1 hour later here. Thank you very much for participating.